Good evening. This is week 6, Thursday. So our agenda for today is shearing stress due to shear force. Before I go on, I have posted the grades for term test 2, and also a thing to take note. So the students that did not pass term test, sorry, not term, the grades for term test 1 is out. Okay. So if your student number is here, right, you have to write the correction, which will be held on June 25th. Okay, 25th. Oh, let me check the date to be sure again. Yeah, will be written on June 25th from 7 p.m. to 9:30 p.m. So these are the students that has to do the correction, and you will do exactly the same question. Okay. And in order to pass or get 15 out of 30, you must score 30 out of 30. Okay, so it's a correction. Correction means you have to, so i.e., if in the correction you score 20 out of 30, you get 10 marks out of 30. Okay, I have to be fair because there are students that attempt the term test the first time. Okay, they might just pass. Okay, so you cannot get more than a grade of 15 out of 30 doing the corrections. Okay, so the correction will be held on June 25th at 7 to 9:30 p.m. That week, there's no lecture. Okay, as I told you all earlier when you started the course, and we go from there. I will tell the location later. Okay. So today we are going to look into shearing stress due to shear force. So just to start this off, so the shearing stress okay, due to shear force is one of the most complex chapter, okay, in structure analysis. Okay, it's very difficult. Okay, it's not an easy topic. What makes it easy is I have come up with a technique, a set of rules that you have to obey to solve problem due to shear force. Okay, and it should be, you should, I hope you would find easy. Okay, so in this topic there are two main formula. So one is known as the shear flow, and the formula for shear flow is Q. Small q is equal to VQ over I. Okay, where Q, as you already know, is the shear flow. And if we look at the units, it's in Newton per meter, or it can be pound per inch. Okay, then V is our shear force. Shear force is in Newton, and or it can be in pound. And then you have Q, which is the first moment of area. And the formula for Q, or the units first, is in meter cube or inches cube. It's not a volume, okay? It's the first moment of area. So Q is equal to A y bar. Okay. And the last term you can see over there is I. Everyone knows I, which is the second moment of area. So the second moment of area is meter 4 and inches to power 4. So what is this shear flow? So if we have a cross-sectional view of our structure, so if our structure looks like this, okay, so this is our structure, right? And then if this is, I'll draw a transformation first. So this is our cross-sectional view. So this is our Y, this is our Z. So we have a shear force in the Y direction known as Vy, okay? So the shear flow, which I will draw in red, looks like this. Okay, as you can see, so this is what we draw as Q. Okay, so I change the length as I progresses. So note that the longer the length, correspond oh, correspond to higher Q value. Okay, so it's the shear flow Q start out small. When you have a bigger area or cross-sectional area, it goes bigger and then it reduces its size. Okay, so that's just an intro for you first. Okay, so this is what we call shear flow. Then the second formula that that this chapter or the shearing stress will look at is our shear stress. So the shear stress formula is tau is equal to VQ over IT, right? So tau represent our shearing stress. Okay, and it is in Newton per meter squared or pounds per square inch. Okay, and T is the thickness of the structure, okay, which is measured perpendicular to the shear flow, okay, to the shear flow Q. Okay, so what do we mean by that? So over here, by looking at the cross-sectional view, right? If you now focus on the cross-sectional view, right? You know the shear flow is vertically coming down. It has to be, as it mentioned earlier, the thickness has to be perpendicular to Q. So if this is our thickness, right? Right, and Q is coming down, so this is where it has to be perpendicular, and this is important for all of you to remember. Okay, so the orientation of the thickness, it has to be perpendicular to the shear flow. Some of you might ask me, what is exactly a shear flow? By looking at the term flow, it's like a fluid flow. Okay, so similar. Q is similar to fluid flow or current flow if you are into electrical. Okay, so it's a flow of current or it's a flow of fluid, so it's equivalent, it's similar. Okay, now I like to emphasize on the orientation that we are looking at in our shear flow and where failure actually occur. Okay, so if we have a transformation looking like this, okay, so this is our transformation. Right, and then if we have a structure looking like this, which has a cross sectional looking like this. Okay, so this is just a sketch of the cross section. So we have this thing, this whole thing is built in, okay, built into a structure like this. Okay, so it's built in. So this structure, if we have a shear force coming down, this is our Vy. Okay. Now, if we were to look at the formula, right, as in Q is equal to VQ over I, and shear stress is equal to VQ over IT, right? The area that we are focusing on, so the area, so Q and A and I, right? So Q is what? Q is our first moment of area. And I is our second moment of area. So the area that we are calculating is, I'm highlighting it in yellow. Okay. So when calculating the area, okay, so this is the cross section. Or the plane. The plane, so I'll write down here the YZ plane in which Q and I are calculated. Okay, so we calculated the I and Q at that plane. Okay, now if we were to get a image of how the structure will fail due to shear, so I have this image over here, right? And I'm going to paste the image over here. Okay. So this is a concrete beam that has failed, and if you were to ask me where is our X and Y, so this is our, based on its orientation, so this is the X, Y, and then we have our rotation Z, right? What you will see is that the fracture, right? So where are the fracture? So you can see here, this is where fracture occur. And if you can look at the fracture, right? The fracture, right? The fracture or the crack propagates in the horizontal orientation, right? You can see majority of the cracks are running horizontal. You only have this section over here that is where the crack meet one another is slightly tilted, but majority of it is horizontal. But in our theory to calculate shear stretch and shear flow, the area that we are interested is on the YZ plane, right? So the crack, if you were to ask me, the crack is propagating in the what? In the XZ plane. Okay, the crack is propagating along the, so the crack is on the XZ plane.